All right, let's move on to a different amplifier configuration. So let's take a look at this circuit. Now I'm going to put the minus terminal on the top for this circuit just because it makes for a more convenient drawing. I'm going to connect the positive input to ground, and I'm going to just show the supplies just to remind you that they're there. All right, this is a 1 kilo ohm resistor. This is a 100K resistor. This is V in. This is V out. Now, how do we analyze this? Simple. We use the golden rules. Can we use the golden rules? Well, let's see. We need negative feedback. If this output changes, does it affect the negative input? Sure it does, through this 100K resistor. If this goes up, this is going to go up. That's going to go into the negative input. That's going to make this go down. So let's apply the golden rules. Negative feedback? Sure. That means that V plus equals V minus. But V plus is equal to ground. So that means, the op amp is going to try to keep V minus at 0 volts. We call this point virtual ground. It's called virtual ground because it's not really connected to ground. But if the op amp is working correctly, it's going to be at 0 volts. It's going to be exactly the same point as ground. Okay, well that's fine. Let's think about how we're going to analyze this. Suppose we apply some voltage here, Vn. Let's see, this is at 0 volts, this is at Vn, so the current that flows through here is Vn minus 0 volts over 1K. That's equal to Vn over 1K. All right, does any current flow in here? Well, it's golden rule says no, says 0 current flows into the op amp. But KCL says that if Vn over 1K flows through here, the same amount of current better flow out somewhere, and the only path it has is here. Well, what's this current? Well, this current is this voltage minus that voltage divided by that resistor. That's 0 volts minus V out over 100K, which is equal to minus V out over 100K. Everybody agree with that? The op amp's got to keep this at 0 volts. If that's at 0 volts, the voltage across here is minus V out, at least in the direction I drew the current. And this current is V out minus V out over 100K. But we know that the current that flows into this node can't go into the op amp. It has to go this way. So that requires V in over 1K to equal minus V out over 100K. Solving for V out over V in, which is equal to the gain, is, well, let's see, that's going to be minus 100K over 1K. That's equal to minus 100. This is a inverting gain of 100 amplifier. So this is the inverting configuration. And you can usually tell the inverting configuration because the positive input is grounded, and the non-inverting configuration, the positive input is usually our input voltage. So I think about this sort of as a teeter-totter. As this goes up and down, well, if this goes up, current flows in here, this has to go down. And of course, if this is a small resistor, this is a big resistor, this has to go down a whole lot more, excuse me, for the same current that flows into this node to flow out. So we can adjust this gain. Let's call this R2 and R1. So the gain of this circuit is minus R2 over R1. Now I'm cheating a little bit. Gain is usually a not assigned value. We would say this is an inverting gain of 100, or this has a gain of 100 and a phase shift of 180 degrees. A phase shift of 0 is non-inverting. A phase shift of 180 degrees is inverting. But we tend to use a shorthand and just call it a gain of minus R2 over R1, which is 100K over 1K, or 100. Similarly, we could change this to 10K. and we'd have an inverting gain of 10. We also call this the summing junction, and we call it the summing junction because the current that goes through here has to equal the current through there. Those currents have to sum to 0. If I had drawn the current in the opposite direction, this would have been a negative current, this would have been a positive current, they would have been equal, and they would sum to 0. I tend to draw it this way because it makes a lot more sense to me that if current flows this way, it has to flow out. All right, interesting question. What is the input impedance of the inverting configuration? Now, the input impedance of the op-amp is infinity, but that doesn't mean the input impedance of the circuit is. Well, that's just V in over I in, but we know that I in, well, this is at 0 volts, this is at V in, so the current through here is V in minus 0 over 1K. That's just V in over R1, which is equal to R1. And that should be obvious when you look at the circuit. If this point were connected to ground, you would say the input impedance looking in here is just R1. Well, this is sort of connected to ground. It's connected to virtual ground. The op-amp is keeping it at 0 volts. So when we look in, we see 1K to ground, R1. So even though the op-amp has very high input impedance, this circuit doesn't necessarily have high input impedance. We can make this resistor bigger. We could make it 10K, but then we'd have to make this 1 meg if we wanted a gain of 100. In general, I don't recommend going over 1 meg for resistors, because then you have to start worrying about op-amp errors. Right now we're considering the op-amp to be perfect. That's a lot easier than worrying about real-world errors. As long as you keep your resistors between 1K and 1 meg, in general, those errors aren't going to hurt you. All right, so that's the inverting configuration. Notice the output impedance is still effectively 0. Even if there's a voltage drop internal, the op-amp is trying to keep this voltage at whatever voltage is necessary for the proper current to flow through here. So any current that flows out into the load really doesn't count. This op-amp is still going to keep this voltage at the same voltage. So we don't worry about what the internal resistance of the op-amp is. The negative feedback keeps it at approximately 0. And once again, that's because of the high gain of the op-amp. And once again, some of that gain is used to get the gain of the closed loop circuit, in this case 100. And then whatever's left over keeps the input errors small. And in particular, this input can't be at exactly ground because otherwise the output would be 0. So there's a small voltage difference here that's multiplied by the internal gain of the op-amp. That internal gain is reduced based on how much closed loop gain we're trying to get. We'll talk about those errors more in the next lesson. Now, let's take this same circuit. I'm going to change this to V1, R1. I'm going to call the resistor here RF for feedback. It's an inverting configuration, so the positive input is connected to ground. And let's connect up another voltage source and another resistor. All right. Well, same analysis. Is there negative feedback? Sure there is. That means that we can consider V plus and V minus to be at the same voltage. So this is 0 volts, virtual ground. The current that flows through R1 is just V1 over R1 because it's V1 minus 0 over R1. The current that flows through R2 is just V2 over R2 because, once again, the other end's at virtual ground. And that means that the current that flows through here has to be it has to be V1 over R1 plus V2 over R2. But it's also equal to minus V out over RF. Minus because the way I've drawn the current, it's this voltage minus that voltage over RF. All right, so V out is equal to, let's see what we got here. We've got minus RF over R1 times V1 plus RF over R2 times V2. This is called a summing amplifier. It's actually an inverting summing amplifier. And the output is just a linear sum of the inputs. And I hope you can see that we could add as many input voltages and input resistors as we want. Because this is always at 0 volts, whatever's happening here doesn't affect here. This voltage causes a current to flow into this node. That current has to flow through here. This voltage causes a current to flow to this node. That voltage has to flow through there. So we could have as many terms as we want. We can scale each one individually by scaling the input resistor. So the advantage of having this virtual ground here is each of these input voltages is independent. Now, this is inverting. Actually, I think I'll leave it as an exercise for you to figure out how you would build a non-inverting summer. But I'll give you a hint that it's hard to do a non-inverting summer that has an arbitrary number of inputs. It's not too hard to do one that just has 2 inputs. All right, let's take a look at other applications. Now, I can show a more generic version. Our minus input, our plus input. We have some input impedance, Z in, V in. We have some feedback resistance, ZF, V out. And we know that V out over V in is equal to minus ZF over Z in. Well, why did I do that? Well, because I don't have to use resistors. I can use other components. Let's make Zn a capacitor. And a feedback resistor. And figure out what V out is as a function of Vn. Well, do we have negative feedback? Sure we do. That means that this is at 0 volts, virtual ground. We know that the current through here, well, I equals C dV dt. So this is I in. So I in is equal to the capacitor. dV dt, well, that's V in minus 0 volts. So that's dV in dt. We know that that current has to equal this current. Well, this is just minus V out over R. So that has to equal minus V out over R. Now we want to solve for V out as a function of Vn. So let's see. That says that V out is equal to minus RC dV in dt. The output voltage is the derivative, inverted, of the input voltage. It's inverted and scaled. It's scaled by RC. But this is a differentiator. It's an inverting. And let's compare that to the RC, the simple RC differentiator we looked at on the second lesson. Now, you'll remember that we looked at this. We said that the output was the derivative of the input as long as the output were small. So V out had to be much, much less than V in. And why is that? Well, because the current through this capacitor is essentially the change in current across the capacitor. Well, if this is too big, we have to worry about V out. As long as we keep V out small, we could say, well, the current through here is just the change in V in. And then that developed a voltage across here. We no longer need to do that here. And we don't have to do that because the op-amp keeps this point at 0. The current through this capacitor is solely a function of changes of Vn. So this circuit fixes the problem we had with the differentiator. Now, let's take a look at another circuit. This time I'm going to put the capacitor in the feedback loop. Once again, it's an inverting circuit. Well, There is negative feedback. Clearly, if this voltage changes, the negative input changes. So we do have negative feedback, except at DC. And the current here is going to be minus dV out. Well, it's d minus V out dt times C. Why minus V out? Well, because the voltage across here is 0 minus V out, and so when V out changes, that causes current to flow in this direction. If V out is negative, that causes current to increase in this direction. Okay, so this current is CD minus V out dt. So if V out increases, current is going to increase in this direction. That's opposite the direction of the arrow. So the current flow is negative V out. So when V out changes in the negative direction, current flows this way. When V out changes this way, up, current changes this way. That means if Vn increases, V out has to decrease to get current to flow through the capacitor in the correct direction. So now let's go ahead and figure out, we've got Vn over R, that's this current, has to equal, we can take that minus sign out here, minus C dV out dt, because that's just a multiplier of minus 1. That says that Vn is equal to minus RC dV out dt. We can move the minus RC over here. Now why don't we integrate both sides, and we get V out is equal to minus 1 over RC, the integral of Vn dt. So this is an inverting integrator. And like the differentiator, it's an improvement over RC. Once again, here we had to make sure V out was low, small compared to Vn, so that the current through this resistor was essentially a function of Vn. Here we no longer have that problem. The op-amp keeps the minus input at 0. The current through this resistor is always a function just of Vn. All right, so we have a differentiator, we have an integrator, and both of them are improvements on the simple RC because the op-amp feedback solves our problem of keeping the voltage across the capacitor dependent on only one voltage and not on both the input and the output. Okay, I believe we are up to another lab. So at this point, I'd like you to do quiz 3, which is a quiz on in the inverting amplifier configuration. And then you're going to go into the lab and you're going to do parts 5, 6, and 7, which are all inverting configurations. When you're done, come back. We'll take a look at the quiz, and we'll do our setup for our, excuse me, our last lab section. And then at the end, we'll do a wrap-up. I'll see you in a little bit.